Radio Spectroscopy and Nuclear Processes Made Easy, Chapter 2, X-ray Spectroscopy. So this is what we're going to be talking about is X-ray and how we can apply X-ray and make a use of it. Pretty interesting stuff. The machine that I'm dealing with is Seiko SEA5120, and it will allow me to play with materials and find out what kind of metals or another periodic table components do we have in that particular specimen. The typical screen would look like that, and it will show the graph and the peaks of the elements of periodic table. That would be your camera screen, which would show magnification of the specimen that is inside the device. That area will show all of the conditions and the voltage 45,000 volts current, and if the collimator is being used or not, or what is the size of the collimator, which would be the opening of the detector. The major application for collimator is to straight out the X-ray photons and make sure that they are coming from not scattered area but primary area of radiation. This is how the device looks like, and we have the device in here, Seiko SEA5120. This part would be liquid nitrogen tank. There is a drawer that is open up. Here we have a camera and part of the electronic, the printer that is printing out the report automatically when enabled, and the screen is not being seen here. Let's go further. Here we have a close to the nitrogen tank, and the camera is in here. That's the drawer. Let's go further. That will be the calibration fixture and two plates with the known parameters, so it could be used also to check out the accuracy. This is the nitrogen tank, camera shown, the high voltage power supply, and there we have, this is the screen, and this is the key for X-ray tube, and this is the main switch. A vacuum pump. When we have a collision with the air molecules, when the X-ray photons strike the specimen, then the part of that energy is being lost. So sometimes it is good or it's better to use the vacuum for it. Electron microscope uses all the time the vacuum, and that's why the results are outstanding. And then we have a specimen. That specimen is our gold plate with given and known information about. Okay, so we have the values. Silver, gold, copper, zinc in the percentage of it. That's how the plate looks like. Okay. And that's the calibration feature. It has 4 different materials and is specifically made for this particular device. And the liquid nitrogen tank. Let's take a look at the chamber again. It's XYZ stage regulated. On the top there is a camera that gives you primary focus on the picture. When the focus is okay, then we know that we can start the X-ray measurement. The door has a seal for the vacuum, so if I want to evacuate the chamber, it's no problem with it. The process that will allow us to find out how much of different components of the periodic table do we have in the dirt that we pick up from the street, or eventually how much of different metals or materials do we have in gold. That process is being called X-ray fluorescence, and we see here titanium atom Ti22. Very nice representation. Some information about the nuclear structure would be that nucleus has a proton and neutron. Neutron is about 1600 times bigger than electron, and it's positively charged, so those two guys between the electron and the proton try to be close. At the same time, due to the quantum requirement, we have shells K, L, M, N, and on shell K we have 2 electrons, then L we have 8, M we have 18, and N we have 32. Some more heavy atoms, they have more shells, but we're not going there. When you provide a radiation from the X-ray tube, that would be the signal from the X-ray tube. It will be a photon. Photon doesn't have a mass, it does have an energy. It will strike mostly the least energetic shell, that would be K shell, and it will create a hole. So then the energy equation would be giving energy E, would be this one. The energy used to knock out the electron would be E0, and the change of energy would be the delta E. Because those guys over there, they have a higher energy level, they see the hole and they try to jump in. But when this is the hole, then another guy wants to jump in. This is the hole, another one wants to jump in. But sometimes they compete between each other, so it's not only that L jumps to K, but sometimes L or M or N try to jump to N. Summary of that screen would be that an electron in K shell is ejected from the atom, and by an external primary excitation ray influence is in the results creating a vacancy on K. In this screen we see the avalanche procedure and the competition. So we have a hole at K, and the electron from L wants to jump into K, but at the same time the electron from M wants to jump to K. So we'll have a scenario from L to K that the change of energy E will be E1 minus E0 equal line K alpha. So by K alpha we would understand the transition procedure. If the electron jumps from M to K, we would have a rate of change of energy, the delta E equals E2 minus E0. This is the E2, and that would create KB lane. The summary of that would be that an electron from L or M shell jumps in to fill vacancy. In the process, it emits a very much characteristic X-ray that is unique to element, and it produces vacancy in turn in L or M shell. At this screen, we have more about the avalanche, and what we could see is M jumping to L, where the K is untouched. So in some rare situation, we have a scenario like that. We might have M jumping to L and E jumping to L without affecting K. Not very often happened. So when M electron jumps to L, we have a rate of change of the energy, which would be E2 minus E1, and that will create a lane alpha. In this situation, we have E3 minus E1, and that will create the L beta or beta, different pronunciation. Those X-rays are very characteristic of in frequency. Frequency could be also described in wavelength. So that's very high frequencies. We don't go to theta hertz, we go just to the wavelength. And that description is enough for the detector to find out the particle wavelength, eventually converted to the graph. A very interesting scenario with Auger electron, when sometimes the energy from E2 electron jumping to E1, energy level that would be from M to L, excites adjacent shell electron, which would be N, to the point of knockout. So knock the guy out. And the rate of change of the energy would be E1 minus E2 minus E3. The summary of the screen would be Auger, A-U-G-E-R, Auger electron. The excitation of energy from the inner atom is transferred to one of the outer electron, causing it to be ejected from the atom. At the screen of the computer, we will see a graph which is made out of the vertical scale, which would be mostly logarithmic, but we could have it linear, which would be number of counts, number of this in the Geiger meter. But that's a little bit different detector. It's a scintillation detector. Not always could be only based on the steady state material or photomultipliers. And in horizontal, we have energy level in kilo electron volts, but we could have also then transferred to parts per billion, parts per million, or how much in a kilogram of grams or milligrams or micrograms of that substance is in the specimen. That's what you see is a representation of how much lead is in cadmium sample, and that it shows all of the intensities, all of the L alpha and L beta line of lead. You see also K alpha and K beta line of lead. Very much straightforward.
But other than that,
How much opening do I have the most? How big specimen that I can put in?
well, as far as here, you can open that in here, and you see it. You know, I can lower it.
Wow, plenty.
It's all the way down. So you
Plenty.
can put from here all the way up to here, all this area.
Plenty.
And it has a big chamber in here.
Yeah.
You can fit the stuff in it.
Yeah.
Okay? But of course it's going to be out of focus because we lower it.
Right.
This one here, illumination, that's to make it bright or to dim it from here, the illumination.
Oh, yeah.
The joystick to move it back the stage, back, forth. This is up and
Could you
down.
move that again so I could
This
see?
is the joystick, you go in,
Right.
move the stage this way,
Oh,
move it
okay.
back one.
I see the picture
front,
changing, right.
Back. This
Right.
is up and down
Yeah.
for the stage.
Yeah. So if let's say I have a specimen that is that long and I want to go to a different point.
Put it in until you see it on the screen and keep moving it until you adjust it.
Right.
Here's the block. You're gonna put it in here, like that.
Okay.
Lower the stage so you don't hit the detector. Push that slowly like that. Make sure that the light is spot on the first one, which is the cross.
Yeah, I see the light.
Okay? And then you just push the machine.
Okay.
Then you go to focus that. Yeah. The camera, if you don't see anything, you put the camera, the image, picture of the camera on.
Okay, so we have a picture of the camera on.
That's
Right?
too big, that's 100%. Usually I make it 75. So
Yeah,
I
we
can
could
see.
switch off the music because it's gonna be on the microphone.
That's the background music.
Yeah, I know. I know.
Then you focus, go with the slow so you don't hit the stage.
Yeah. Make sure that I don't hit the stage.
Up until you see this.
Yeah.
Then you go here. Make sure you come to the fourth corner here. On
The
this
fourth
side.
corner left, down.
If you have it wrong, the machine will correct it for you.
Right.
But before you do that, you have to go to this icon in here.
Okay.
It has like 2 files. You open that, and you go for maintenance.
Maintenance. Okay.
Number 6.
Okay.
And that's the first one here is the intensity correction.
Okay. Right.
It's gonna be okay.
Okay.
The machine will move automatic to that
Wow.
pink color, and the vacuum pump will start.
Right.
Boom. The same thing. And the last one is the resolution.
Yeah. Well. Yeah. Yeah. Can we have a whole process of normalization on the camera?
Sure.
Yeah,
If
okay,
you
so
want.
let's start.
I'm
Yeah.
gonna open that again, and I put the jug in. And you see, as I'm here, it's too low, down low. So I usually just try to raise it to save my time to know where I am. Okay, and then I move that until I reach the light, at least, so I don't go crazy.
see the light.
Try to see where is that cross, right?
Yeah.
So I got it here on the cross, and when I close that here, close it.
Yeah.
It should show it here, but I raise it. I make it so bright so I don't see it.
Okay.
So I'm gonna go here.
So this
until
is the
I see
right button.
raise it a little bit fast because I can see this here. You see this here?
Yeah.
If that hit here, that means I hit the head.
Yeah.
So that indication.
Oh, that indication
it
is the
shows
height.
you where you are, right? So if
Right.
I go a little fast in here, you see now?
Yeah.
Now it's showing. So now I go like that, keep
Yeah.
moving it until I get
Yeah. Make sure that this dot never go
about to
up.
touch that.
Touch.
It will machine it will stop, and
Yeah.
then until you hit correction, you have to go correct
Yeah.
it ahead.
Yeah.
Okay. So this is now I got it in the center, and I'm gonna go start. When I go start, and it said okay.
Uh-huh.
I click OK. But it moved. But it happened that came
Yeah.
right in there. I
Right.
gotta make sure, as explained to me here, that
Right.
the arrow gotta be in that corner.
Right.
Got it?
Yeah.
And then I'm gonna say OK. And I highlight this, and I click OK
Right.
everywhere. Right? So we're gonna stop that also, right?
Right.
Okay. And then I gotta take the vacuum off because it was running. And when we finish with that, we took the last step, which is the resolution.
Okay.
Click on resolution.
So we turn the vacuum off right now.
Right. And they start again.
Start again.
And it's okay. It's gonna move to the resolution, which is the last step.
Right.
And you're gonna tell you start, adjust the sample, you said okay, boom, it will start, and that's
Okay.
finished.
At that point, I'm
The
not adjusting
normalization.
anything. It's gonna do automatically.
Nothing, everything is automatic.
Okay.
Normalization, okay?
Okay.
And it will start counting the time. Shall I stop? Or you wanna finish?
How much time is gonna take?
96, 80.
Let it finish. Let it finish.
If any time you wanna stop the machine, it's right here. See this guy here? It says
Yeah.
abort. It will
Okay.
stop.
Okay.
Okay?
Mhm.
Or
Oh, we
stop.
see Meganium already.
Okay. So that's the main thing that I do. I normalize that every Monday morning.
Every Monday morning,
And
once a
it
week.
takes 10 seconds, 100 seconds.
Okay.
Okay, so there's nothing else I can do with this. Like, time is clicking in here.
Yeah.
Okay. 1 second, and it's done. Okay, now the resolution correction is completed.
Okay.
And that's okay. And then now you go in here, this icon is an application.
Yes.
Click on that, and I usually use the bulk analysis for the element.
Okay.
And I put you on the bulk, you can move this in here, and you start putting the sample.
Yep.
I'm gonna leave this in here so you don't lose it.
Okay.
The movement, you know that it's in here.
Okay.
When you go to your office, just to take it off and
Right.
keep it in a box or something.
Yes, yes.
And when you put the sample, you take the sample, put it in here under the light,
Right.
you close,
Right.
and again you can see here, focus it, not focus it, right? And
Right.
just start. When you push start, it starts leading. Okay? If you have,
Hold on. Okay, no. Hold on. Josh.
and this
Okay.
is start, not this. This will start the computer, but this will start the machine.
Okay, start.
Right.
Yeah.
Now, if that icon for the printer is on,
Right.
every reading you take, it's automatically going to print
Okay.
on the machine. If
Okay.
you have it off, if it's not highlighted like that, this
Right.
is on.
Right.
This is off. It's not gonna.
Okay, so when it's highlighted, it's off.
When
It's on.
highlighted is on.
Okay.
When it's off. Now it's off.
Yes.
Right?
Yeah.
If you want, say, this report you want to print that report. Usually I go in here,
Yeah.
the quality analysis mode,
Okay.
and I pick what I want to do. If you highlight cadmium,
Right.
if you highlight silver,
Right.
zinc, anything you highlight here, and it said recalculate on FE. This is the recalculate. You can see a picture of the calculator in here.
Right.
It will do it, and it will print the report.
Yes.
When you click on it, it will open all that. So on this one here, you can go to maintenance,
Uh-huh.
and now to maintenance, upgrade, how long you want to add liquid nitrogen. Upgrade it, update it, or just to forget it. Don't let the machine, I want to tell the machine, don't remind me to add liquid nitrogen every Monday, say.
Okay.
Okay? Or no, I wanted the machine to remind me.
So
every
there
Monday.
is a sort of calendar.
It's exactly, to
It's
keep,
calendar, right.
to keep that stuff, okay?
Spectrum, routine, bulk, film.
The analysis in here,
Yeah, analysis.
whatever you want to analyze for, I think this is no, because everything you need the vacuum in here. If you want something, yes, then you can put it on. I think it will work. You know what I mean?
Yeah, from sodium, and can you go down? It should go to uranium. From yeah. All right.
I think it just take everything in the periodic table to uranium.
Yeah. Oh, it says gold because it was last time detected.
Yeah.
Okay.
Okay?
Yeah.
So this is the icon.
And can you come back to that menu because?
But if you want, but in the morning, you wanna normalize the machine.
Right.
When you come Monday morning, it's calibrated for every Monday morning.
Right.
The machine gonna tell you did not do the normalization.
Okay.
You did not do the
Yeah.
normalization. Then you remember what it is. If you click on that, it will take you to the method. Let me take this one out.
That's the calibration.
Very fragile. I don't want you to destroy that because this one here, it's a very like a compound or something.
Right.
So be careful with that.
Yeah, I gotta be careful with that.
So I want to measure this sample. So I'm going to go in here, put this sample in here. I just want to make sure that the light is on top of it. So
Yeah, the light was already adjusted with.
so I don't have to go crazy, look for it for the sample, right?
Yes.
See it?
Yes.
And then if I push that in here, make sure the camera is on so you can see it. And when I push that, you want to see it in here.
I
You're
get
going
it.
to see that the picture is coming on.
Yeah. That's it.
But it's out of focus. So you can go in here, again, slow. Usually go with the slow so it doesn't hit anything. Okay? That's nice. It should be much perfect than that. And then this measurement in here, how long you want to measure? I'm going to do it fast so you won't run out of time. So I'm going to do it for 10 seconds.
Yeah.
10 seconds, and I say okay. And I hit the start. And you're going to hear the machine go pick. Here you go.
Yeah.
And you're going to 10 seconds. And once you start the measuring, you're going to see the peaks start to show. Here you go.
Yeah.
And you can make it, you can extend it like that. You can move that on the side.
And it's already labeled.
Already labeled. So this is here, the nickel,
Yeah.
the green, zinc,
Yeah.
and that's a little platinum. I think that's here, or palladium. I'm not sure, but I don't think it's platinum. Platinum usually comes next to the gold.
Uh-huh.
Gold, and all the way here is going to be the silver.
Uh-huh.
And that little bit in here probably is palladium. Probably.
Mm-hmm.
Usually it's come right here. But that's the silver, the gold, and this is the zinc, it's
Yes.
labeled, and this is the nickel, and the iron. That's it.
Yeah.
And you can see it. And they give you the reading in here. Now, say from this reading, I said to myself, you know, that nickel is actually, it's too little nickel. So why do I need the nickel? I'm going to take the nickel off.
Yes.
So just take the nickel, I'm not highlight the nickel, right?
Right.
And I said recalculate. So give me the reading with no nickel. But of course, being everything has to add to 100%. So take the nickel sometimes, take the nickel, add it to the gold, or add it to the silver. I don't know what it's adding.
Yeah, yeah.
Okay.
How about if we put all of the table, highlight all of the table?
Yeah, go ahead. If you want to say, I don't, you know, I want to measure
everything.
I want to measure nickel. I want to measure palladium, platinum.
Oh, can we highlight everything?
Oh my God, it's going to take forever.
Oh, okay, because
Cobalt, iron, magnesium. You see how much I'm going to put?
Yeah.
And you can just play with
Oh,
that.
okay.
All that, right? And I'm going to say recalculate.
Recalculate.
Right in here. It's going to give you a big list.
And it says 0, 0, 0.
No, it's going to
Oh,
read
yeah.
it down here.
Okay.
It has, you see, but iron is too small, and the cobalt is too small. Nickel, it's okay. But all the other stuff is insignificant.
Yeah, insignificant.
Yeah.
But it, yeah, it's beautiful.
Keep adding, and it will read it. That's
Yeah,
the beauty
yeah,
about
yeah.
this. That is, you tell me why this and not this. But I don't need
Right.
all this. It's more flexibility on this machine.
Right.
Believe me, it's serious. I love this machine. And it read, and it's not nothing more. The machine is perfect.
The first time you get to electron microscope, you're gonna sell everything. They have right now the electron microscope that is has.
But you see this here? You see here? It's labeled everything in here.
Yeah.
Okay. You see the problem is this. You see the problem here?
Mm-hmm.
You see the platinum?
Yeah.
How it becomes very close to the gold?
Yes.
That's the problem we have. That we cannot differentiate between them.
Well, no. You actually see, it's not added. This is the separate peak.
I understand
What
that.
you can do is widen that.
We tried that before. I even asked him to put a fake peak in between them. He couldn't do it.
No. That should be a way to spread it and look at the individuals. Not just move it, but spread it. Yep. Go ahead. Go further. Go further. Now you see the individual.
I know, but it's still touching.
Let me explain to you something. When you have a nuclei, in the nuclei you have a proton and a neutron.
Yeah.
Neutron by itself is a neutron doesn't have a charge.
What's the camera? Okay.
Yeah, it's okay.
fine?
Yeah, it's okay. And neutron has no charge. The proton has a positive charge because each one is going to give the photon,
Right.
and the photon is an energy.
Right.
Only doesn't have a mass.
And that's why we have that liquid nitrogen to cool down the detector.
Well, the thing is that you have to have two things. At first, the bigger the vacuum, that's why I suggest you to go to the electron microscope, and I'm telling you it's inexpensive. Okay, never buy the new one. It's going to be expensive. So, at first you need the vacuum because you don't have the molecules of air.
Right.
The electron microscope is giving you the vacuum, and you're not dealing with an X-ray.
Oh.
So at that point, you're not worried about that X-ray being damaged. X-ray tube. You're dealing with an electron gun.
I see. Okay.
Okay, and that electron gun is actually hitting the specimen, and that specimen is giving the photons of.
So I can read that gold sample under vacuum.
100 times better.
If I do that and it comes better, I'm going to change my mind about buying a machine.
Oh no, not this one, not this one, not this one.
Okay.
This one is incapable of doing.
For that, we leave here at 4 o'clock.
Okay.
I want you to have time to.
Yeah.
But
Okay.
you see how we change that by clicking on this, and they get the periodic table, and they highlight everything we want,
Right.
and it will read it. However, it's a significant reading or not significant reading.
Right.
That's up
Right.
to you to decide.
Right.
Okay.
Yeah.
What else? That's basically what it is.
Here we have the elements listed here. So it goes from sodium to uranium all the way down. Oh, now it's better. From sodium to uranium, and it shows that is from K shell of the atomic structure. So we have the closest shell to the nucleus, K, then it's L, M, N. It requires vacuum for sodium, magnesium, so everything that is red, you have a chemical formula, and then it goes cobalt. Yeah, cobalt will be imported for Kalman measurement. So the basic application is to be able to see the changes when the cobalt compound is in the tube and is being exposed to the radio wave from 300 to 450, 500 megahertz to see what changes do we have. Well, this device is not able to show the chemical bonds, but it is able to show the periodic table elements. If there is any changes, I will be able to see that. Also, when I hold it like this and increase the size, I'll be able to have already labeled contents of that specimen, which was similar plate to this one. Oh, it's not showing sharp. And of course I can have an image, adjust. So you see the slight line in here. It might not be very much visible. I can increase a little bit the picture, so it would be. So I'm trying to adjust the sharpness, and this is the maximum sharpness. This is not to entertain me with it, but actually focus to the best position of an X-ray beam, and then can minimize it, make it smaller. I was making a measurement with the vacuum, and there was a composition. Right now it is showing me the percentage of the specimen, so that would be 9.49% white of nickel. We have zinc, gold, and copper. The conditions are time 50 seconds, which is plenty, voltage 45,000 volts, current 8 microamps. It's collimated. That means we're dealing with X-rays coming from the specimen that would be not aligned. They're not gonna go to the detector. And environment is vacuum. I'm gonna go here one more time so we could see much better and show how that works. So here, nickel, zinc. There is a one peak present. I couldn't specify it, but also I have a table that shows me all the condition, all the measurement values here. There is one in this point which wasn't specified, but if I try to highlight more of it, eventually I'm gonna find, okay, I found something in here, and I'm trying to get to this point, see what we're gonna get. Okay, got it. So we have the spectral components. Now I'm gonna recalculate, and soon we will see the values of those additional peaks that were not recognized. It takes a little more time. Now we got it. And try to pull it in more, so I can pull it like that, spread it more, and then drag it all the way. It could show me percentage-wise, but also it could show me in kilo electron volts, which would be the energy level of those peaks. Those peaks I didn't recognize yet, and you've seen some other peaks. They are in different color. I gotta look closer, but I think I have a palladium, I have a platinum, I have a gold, and definitely lead. So let's go here, like that. There we go. And if we got lost with that, you can go all over the table with all values specified. And I'm gonna try with those elements. Go with this. Okay, so we have another one. Unfortunately, this one will be blank. There is a friend of mine all the way in Europe who's gonna see that video, and to whom that video is dedicated is gonna tell me more about it probably. Okay, we've got a little bit here. Pretty nice. We have one here, not recognized. I put uranium, but uranium is not present in this specimen. Also, for the purpose of Coleman free energy device investigation, it's good to have this device, because there would be a proof that no radioactive compound was utilized. So the science is opposing the fact that under any condition it would be possible to have non-radioactive substance or elements to become radioactive by an influence of the radio wave of 3 to 450, 500 megahertz. And let's start. Whoops. I think I've got a crash. Let's see what's happened. It looks like my power supply didn't hold the load. And now everything is starting. Let's see how the system behaves after the crash. Okay, I think I have to switch the computer. Yep, got it on. And let's see. It recovers. Interesting experience. Okay. Yep. It did recover. So I know that another experiment I have to do when I have stronger UPS, and the UPS is in here, down here. Okay. The friend of mine came with a gold that he melt, and he add some additions to it, and he wanted to check my machine, and I put it on test, and that is what I've got. Zobacz, tu jest vacuum chamber, jest seal.
Wow, wow, wow.
That's it. See? Okay. Now, what you're gonna do is
No drilling, no nothing. Just
nothing. What we do is now we adjust the specimen, so we want to go to more or less this area of the specimen, and we adjust the sharpness. Now we adjust the sharpness, and let's go. So the machine is starting right now, and we're gonna see the picture exposed. But I'm gonna switch to this kind of string, I like it better. And soon we see the reading. It's gonna take approximately 43 seconds more, and we're gonna have the results. I can also adjust the vibration. I can also adjust the peaks, so we can see the growing peaks better and have control over what we're getting, like that. And we see the zinc from Ka line. We have Au for LB line. Right now, the end of the line is 29.89 kiloelectron volt and starting from 4.57 kiloelectron volts. It's 0 second, and now we have the measurement. Okay, 1.73% of iron, nickel 0.4%, copper 28.39%, zinc 9.57%, palladium 0.95%, then we have a gold and 45% of 78 is gold, and silver is 13.54. Because the total number has to be 100%.
yes.
So when I discovered those peaks, the measurement a little bit changed. So I'm gonna try to find what we have here. This line shows me something present. If we take the traces, which are negligible, we still have Ag, which would be 12.44%, which would stand for the silver. Ag is the silver, and Au is the gold. So when you go for the gold and you put all of those additions, small traces of it, so nickel is 0.36, 1.58% is iron, then you have a silver 12.5%, you have a 40.68 of pure 24 karat gold. So here end of part number 2 of radio spectroscopy made easy. That was X-ray spectroscopy based on the device that I was able to acquire for the purpose of investigating free energy device from 1956, Coleman, that is supposed to produce 1.2 kilowatt of energy for 70 years. So we have two news, one is bad, one is good. The good thing is that I have seen the device producing electricity. The bad thing is that I'm still trying to get all of the imaging devices that are needed for that project to be working. Again, free energy is the energy that is free of charge. Energy must come from somewhere and be converted to usable form of the energy. But there are only few percent of population of this earth who wants to make all of the money and want us to have as little as is humanly possible to produce more and more for them.